Good morning, students. Today we will be conducting some simple activities from the chapter Electricity. We have studied different concepts in this chapter. We have studied what is an electric circuit. We have studied about conductors, insulators, resistors. We have studied how to measure potential difference, how to measure current flowing in a circuit, how to start or stop the flow of current in a circuit. All these things, just to get a theoretical understanding of these concepts, is not good enough. So today we will be constructing some simple circuits. Let's begin with a wire, then a cell, then let's connect one more wire. Now this is going to be a very basic circuit with a switch. Now we have studied that what are the basic components of any circuit. Now we are trying to begin today's activity with the construction of the simplest circuit using wires. As you can see, I'm connecting the wires one by one, then an ammeter. Now this is to check what is the current flowing in the circuit. Then let's join one more wire. Okay. After that I will connect one bulb. Now this will indicate the flow of current in the circuit. Let's connect a wire and put this on the other end, and let's just bring the other end. So now that the switch has been closed, you can see that the bulb has started glowing. Now just check the values. It's a 9 volt cell. The bulb is having a resistance of 10 ohms. So what should be the current? Using Ohm's law, we can find out current. V equal to IR. So current should be V by R, that is 9 by 10, so 0.9 ampere. So you can see the current is being shown by the ammeter. Now the direction is the conventional direction of current, as you can see. The direction in which current is considered to be flowing in an electric circuit, that is from the positive to the negative terminal of the cell. So this is the direction of conventional current. So it's the simplest circuit, having a cell, a conducting path made up of wires, and a switch. Now just to check the current flowing in the circuit, I have joined one ammeter and the bulb. So this is one simple activity. Next, I have removed some of the elements, and now I will be joining two resistors, each of value 10 ohms. Just see how I have joined the resistors. One end of one resistor is connected to the other end of other resistor. Like there is only one common terminal between the two resistors, isn't it? Now the switch is still open. This is how a series combination looks like. See, once the switch is closed, current starts flowing. But one thing you may observe, that now the current measured by the ammeter is 0.45 ampere. What is the voltage? 9 volt. But the resistance in the circuit is now 10 ohm plus 10 ohm, that is 20 ohms. So again, using Ohm's law, V equal to IR, we can find out current. Now this is a voltmeter. Let's use this voltmeter to measure the potential drop across each resistor. Let's just put the terminals, adjust it a little bit. Yes, so you can see that the reading is 4.5 volt. 4.5 volt across the first resistor. What about the second one? Again it is 4.5 volt. So you can see across each resistor the potential drop is 4.5 volt. So 4.5 volt plus 4.5 volt, that gives a total of 9 volt, and that is the voltage, that is the EMF of the cell connected. It is showing 9 volt. So this means that when two resistors have been joined in series, then across each resistor there is a potential drop of 4.5 volt. So this means that in series combination of resistances, the potential drop across each resistor is different, but same current flows through the resistors. Next, I will be joining these two resistors slightly in a different way. Okay, can you figure out the difference? See, now both the ends of the resistor would be connected to each other. Okay. Yes, somewhat like this. This is the combination that is usually referred to as a parallel combination, isn't it? Now if you remember, in the previous case the current was how much? 0.45 ampere, and just check the reading shown by the ammeter this time. It is 1.8 ampere. What is the equivalent resistance right now in this circuit? 10 ohms and 10 ohms. So 1 by 10 plus 1 by 10, that is 2 by 10. So you take the reciprocal, so equivalent resistance comes out to be 5 ohms. So V equal to I into R, so I should be V by R. V is 9, R is 5, so 9 by 5, that gives 1.8 ampere. So this is a parallel combination. In a parallel combination, you can see, as the ammeter itself shows, that current has got two paths, two separate paths. This means there is a branching, there is a division of current taking place, and through every branch different current is flowing. Now let's check the potential drop across each resistor. See, it is showing 9 volt. This means, as in the previous case in series combination, the voltage drop across the resistance was 4.5 volt, not equal to the EMF of the cell. But in parallel combination, every resistor is working on the same voltage. See, it is 9 volt. So obviously, if you are asked to compare between series and parallel combination, you can very easily say that in series combination, same current flows through every resistor. The potential drops are different. But in parallel combination, there is a branching of current, and every resistor is working on the same voltage. The potential drop across each resistance is same. Now let's just include the resistance of the cell. See, I've used the value of 3 ohm. I have including the resistance offered by the cell. It is called internal resistance. If I include that, obviously it will produce an effect on the current. The current has reduced to 1.12 ampere. Okay, so by changing the battery resistance also we can control the current. This means battery resistance has also got effect on the current flowing in the circuit. Now let's alter the wire resistivity. This means the resistance of the wire, the material, if that varies, or if the physical conditions that is affecting the resistivity, obviously that is temperature, if that is varying, even that is going to produce a significant effect on the value of current flowing in the circuit. You can see I'm changing the values of resistivity and how it is affecting the current flowing in the circuit. So in this manner, very easily we can understand. Now let's use these circuit elements to complete this circuit and try and understand how current is affected by the resistance in the circuit. So you can see I have connected the same cell of EMF 9 volt. There is a key. So now there a 10 ohm resistor is there and a bulb of again the 10 ohm resistance. So the current flowing in the circuit is 0.45 ampere. I've kept an option to connect more number of resistors. Let's check the voltage across the bulb. It is 4.5 volt. Can you identify the type of combination? What type of combination is this? The bulb is also acting like a resistor. See the voltage across the resistor, 10 ohm is again 4.5. So very quickly we can understand what type of combination of resistance is this. Of course, it is a series combination because there is one common terminal between the two resistors. Okay, so this is one such circuit where we can see how the elements have been joined in series and how that is going to affect the current. Now let's just connect one more resistor. Okay, so I have joined one more resistor of 10 ohms in parallel. So now just see the potential drop. See, the EMF of the cell is 9 volt. So across the resistance it is showing 3 volt, isn't it? What is the current flowing in the ammeter? It is 0.6 ampere. Can you very quickly do the calculations? What is the equivalent resistance in the circuit? There are two resistors of 10 ohms. So the resistance in this part should be equivalent, should be 5, and then there is a bulb of 10 ohms. So the total resistance of the circuit is 15. See, the potential drop across the bulb is 6 volt. So if there is a 15 volt resistance and a 15 ohm resistance, equivalent resistance in the circuit, and a 9 volt EMF is being given, so V equal to I into R. So obviously it should be how much? 9 divided by 15, so that is 0.6 ampere. That was the current. Now altering the resistivity, we are checking what dependence we can understand the relationship between the potential drop and the current. See, I am varying the resistivity of the wire, and you can see the potential drop across the 10 ohm resistance as recorded by the voltmeter is directly proportional to the current measured by the ammeter. Just check the values. See, voltage is 3.57 volt, current is 0.35, isn't it? See, 9 volt voltage, current is 0.9 ampere, 7.39 volt is 0.74 ampere, 6.13 volt, that is 0.61 ampere, 4.43 volt, that is 0.44 ampere, 3.48 volt, 0.35 ampere. So you can see that the potential drop across the resistor is directly proportional to the current. As the resistivity of the wire is changing, or you can say as the resistance is varying, resistivity is nothing but specific resistance. So as we were altering the resistance, the physical conditions were altering. This was giving us a clear idea of the dependence between potential drop and current. Okay, thank you.